All right, we're picking up right where we left off last time. And the question is, how do you write a program that does something or not, depending on some condition? So write a program that if R20 is equal to R21, then you add 1 to R22. First question is, how do you add 1 to R22? The increment instruction. So the next question is, how do you test if R20 is equal to R21? Well, there's two ways to go about looking at the flowchart. This should be a review from last time. Which one of these is the better way based on what I told you last time? Yes? Looking in what direction? This way. Okay. This one. It's better because yes is what's going to cause a branch. If something is true, it will branch. That's what a branch instruction does. So we'll be branching past some code. So one of the things that flowcharts and embedded design really try to do is not only tell you what's happening, but also in what order the statements should be written. So you're going to have your test, then you're going to write your increment, then you're going to have a label, okay, called something else. So here it is. Here our test is actually subtraction. Almost always our tests are some kind of subtraction. So we say subtract R20 from R21, which implies that there is some order, okay? If it's subtract A from B, then whatever your situation here, this will be A not equal to B. If this was greater than or equal to, it would be A greater than or equal to B. So when you actually replace those symbols, it's A greater than or equal to B. If you swapped them, R21, R20, then it would swap the order. You would swap, so you would get B greater than or equal to A. Okay, so that's where we left off last time, I think, just about there. So your turn. Let's start with, can you remember what we were talking about last class? Can you draw a flowchart? I'm not even asking you to write code. Draw a good, easy to implement flowchart, okay, that will increment R22 if R26 is less than R24. So the flowchart, I won't fill anything in here. It's going to look something like that. So you fill in what the condition should be. You fill in where the yes and the no should be. Right? We're doing this in 2 steps. Don't jump ahead to the code yet. I didn't get any coffee this morning. Oh, this is going to be a rough lecture, guys. No coffee. All right, bring your attention up front for a moment here. So the things that I know need to happen are increment R22. R22 needs to increment. Now, what I know I want to have set up is the yes branch jumping past that and the no branch not happening. So I take my test, all right, if, excuse me, R26 is less than R24, and I invert the whole thing. I say, all right, when this is not true, I want a branch. When is that not true? When is R26 not less than R24? Not quite. So let's go back many moons. Everybody remember your number line? What does it mean if I have a filled in bubble and a line going to the right? Less than or equal to, right? It's all the numbers including that number. What about an open circle going that way? Greater than, but not including. So if I have R26 less than R24, the opposite of that, this is just open circle. So if I were to just switch it around, greater than I did write greater than, right? R26, R24. That still doesn't include the spot. So the correct opposite of less than is greater than or equal to. Intuitively, like you see it in hindsight. Yeah, well, obviously, it can't just be that because it's missing the number when they're equal. So the question is, when do I want to branch? When R26 is greater than or equal to R24. So I can write that, R26 greater than or equal to R24. Everybody good so far with that? All right. If you wrote, let me clear out some of this ink. If you wrote this right here, this is not a good solution. This has the no branch going out. That's not when things branch. Okay? So here it is, greater than or equal to. Don't use a branch that has a no coming off the side. It doesn't end well. So the code, all right, the next question is, do we have a branch that will test greater than or equal to? I see some people already have their ASM sheets out. You're going to want that handy anytime you're writing code. So yes, there is an instruction. It's greater than. And here they write it down as carry clear, which is the same as a same or higher. I prefer that you write branch if same or higher because it implies meaning. Excuse me. So it branches to this label L1. So it branches past the increment. Question?
You also use branches greater than.
You could have. The difference, well, you tell me what the difference between same or higher and greater than or equal to. We covered this last class. Signed numbers. This is for unsigned. Excuse me, I'm recovering from a cold. And this is signed numbers. So if you have both positive and negative numbers that you're comparing, remember signed 2's complement uses a 1 in the most significant bit to indicate negative. So greater than or equal looks at that and determines the sign and then looks at the magnitude. Whereas unsigned just looks at it as if it was a positive number. Okay. So the problem with this next question, write a program that if R26 is greater than R24, increment R22, is, yeah, we correctly can say, all right, we understand that we want to switch that so that the branch goes around. And the opposite of greater than is less than or equal to. Everybody agrees that the opposite of greater than is less than or equal to. But in this case, we do not have a mnemonic for less than or equal to. And I think I made a pretty big deal about that last time. Oh, God, how could they? Oh, the humanity. Well, the truth is that R26 less than or equal to R24 is the same thing as R24 greater than or equal to R26. They're the same. And we do have a greater than or equal to mnemonic. So if you have a case where you find that you've made your flowchart correctly, and yet you do not have a mnemonic that will fit that, swap the order of the arguments. And you change the sign. So, okay, there it all is. And I got to erase the ink so you can see the final code. So the final code here even though we say, all right, did I swap it? I did swap it. Oh, very subtle thing happened on the slide. I went 26 less than or equal to 24. Then you swap it. R24 greater than R26. And again, the order is implied in the subtraction. So here I say same or higher, again, using unsigned. If I wanted to use signed numbers, I would use GE, BRGE, greater than or equal to. And that takes care of if. If this, then that. There's another kind of conditional execution. The if else. This says, if this, do something, otherwise do a different thing. For example, if R20 is greater than R21, increment R22. Otherwise, decrement R22. Doesn't matter what the condition is saying. This is just a toy example here. But we're saying, all right, we're going to do one of two things. We will definitely be altering R22. The last piece of this that is in this example is there's something that happens before the if-else. Is this right here? That's the if-else. There's something that happens before, and there's something that happens after. Regardless of how we alter R22, we're definitely going to increment R17. So with all those pieces, let me present to you a flowchart. Okay, R17 equals 5. Then we go into our conditional. If R20 is greater than R21. Now here, I've broken my own rule already. I said always make sure that the yes jumps past some code. And I always did that by making the yes come out to the right. But I actually haven't. I have not broken my rule. My rule is always make the yes jump past something. Here, the something I'm jumping past is the decrement. If you've ever done flowcharting in previous courses or even in brainstorming, typically you'll see something like this. Yes, no, and then finally. You see it written side by side here, as if the yes and the no choice were equal weight. Well, in this course, we're not going to do that, because we eventually have to end up writing the code line by line. And if we're going to write the code line by line, I want to know what order to write my code in. So my code that I'm going to write for this, notice I've colored a few things. I've got a purple line, I've got a blue box, a red box, an orange line, a green box. Those are all going to correspond to this code. So here, I say subtract R21 from R20, which means I'm comparing R21 to R20. And I do a branch if lower than. Again, carry set is the same as lower than. So this is saying, all right, branch, undo. If R21 is lower than R20, which is not quite what I have written here. I have written R20 greater than R21, but I think we've seen at this point you just swap the order because we don't have just greater than. We have greater than or equal to, we have same or higher, but we don't have greater than. So you have to swap the order of the arguments. And then the lower than is what tells us what our condition is. So we're going to branch to the if label. We branch down to there. Oop. So that's why it's a purple line in the flowchart, purple line of code in the example. But what is that doing? It's passing over this block of code. Now this block of code, if I don't branch, both of these lines are going to execute. So it's going to decrement. So this is the no branch. The no branch is what we call a fall through. It's just the program counter keeps incrementing by 1 instead of being overwritten by the conditional branch. So it falls through to the decrement. And here's where the magic of the if-else is. It jumps to next. Now, jump is an unconditional. It's always going to do this. But we need this statement because if we didn't have this, we would decrement. And then what would be right after that? Well, if the jump wasn't here, we would go into the if label. So we decrement R22 and then we increment R22. That's obviously not what we want to do. That's not helpful at all. Because if you increment and then decrement, you haven't done anything. Except waste some cycles. You've wasted some processor cycles. So you need that unconditional jump to jump past the red block. So let's just look at all of this. When I wrote this, the purple line was first, and it's the first line of code. Then the blue block. There's my blue block of code. Then here I've got my yellow branch. Third line of code. Excuse me. After that, then I have my red block of code, which is my if label, and then my next. Now my next is going to execute regardless. Okay? There's two ways of getting to next. This line right here. There's two ways. First, if I do the initial branch, I branch to the if label, and then I fall through to next. Okay, because it's linear at that point. If I don't do the branch, I fall through to the decrement, fall through to the unconditional jump, and then I skip the red block. So either way through this code, whether you do the conditional branch or not, because that's the only choice that's made, that purple line. It's the only place where something could go differently. Okay. Regardless of whether that goes to the blue block or the red block, only one is going to be executed. It does not matter what is in the blue block. Could be 100 lines. Could be one. Doesn't matter what's in the red block. Again, could be many, many lines. Okay. What is important is that it's a contiguous block of instructions. Okay. So that is an if-else. And I really encourage you to always practice this type of flow charting. Put one above the other. The yes branch always goes past the first block. The no block is what falls through. When you go from the higher block, to get past this block, you have to do an unconditional jump. Okay? You can write any if-else statement using this basic template. All right? Yes?
So the branch if carry set is causing it to...
So branch if carry set, this is why I had you write it down right at the start of class. Ignore the fact that it's branch if carry set. Just write it down as branch if lower. Branch if lower is much easier to understand. I leave it in there as an object lesson to why it sucks so much, right? But I've got the comment right there for you. So when you go back and look at this, branch if carry set is the same as branch if lower. So that's saying, all right, if R21 is lower than R20. Why would you want to do this? Well, because sometimes you're actually looking at the carry bit. You're not looking at whether or not two numbers are related to each other arithmetically. You're looking at the carry bit for reasons. When we get to chapter 5, we talk about some instructions that will modify that. All right, so that's if and that's if else. You could extend this to multiple if else's, if this, then else, if this, and so on and so forth. But it's all application of this basic flowchart. The last kind, well, second to last kind of non-conditional execution, certainly if we're using conditional branches, is the loop. And again, I've got a very nicely colored flowchart because at the end of the day, it's not too difficult to deal with. All right. Now, having given back 2 skills tests, maybe we need to spend some time on this. Write a program that executes this line 9 times. I'm going to tell you that if you want to do something n times, load up a variable with that number of times. Okay? We typically call these different blocks the initializer, or init, the body. The body of the loop could be many, many lines, but in this case it's just one. Then we have some kind of update. The update somehow affects the counter variable. Then we have our test. Now this test says R16 is greater than 0. Sometimes it's worth looking at a test like this to see if maybe there's another way we could write it, but we'll get to that. So I've got initializer, body, update, and test. All loops can be broken down into this setup. Sometimes the initializer is going to be empty. Sometimes the update might be empty, or it might be a side effect of the body. Okay? So here's my solution to writing a program that executes an instruction 9 times. We load 9 into some variable. We have to choose R16 to R31 because it's LDI. It's an immediate mode instruction. I put a label at the start of the body. My update for this is just decrement. So I load up a number 9 into a variable, and then each time through the loop, I decrement it. Now here, my test says greater than 0. But since I'm only decrementing by 1, it's going to go 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So the first time through this loop where I won't be branching is when it's 0. Well, think about a decrement as a subtraction by 1. Right? So when our 16 is 1, we subtract 1. That gives us a 0, which means our Z flag should be set. So here, rather than saying, all right, we've got to load up 0, then we've got to compare it or subtract it, we're just going to use the branch not equal to. George, can you do me a huge favor? Like the hugest of all favors? Can you go and get me a coffee? Because I'm dying up here. Okay, I'll pass those out at the end of class. It's probably $3. What? What? Oh no, it wasn't. It was $2.64. You're all $2.64. What do I want in my coffee? No shot of espresso. It was a Boolean.
You said 2 creams, 2 sugars? 2 creams,
Well done, guys. Proud of you. Everybody gets a bonus point for the day.
Wow.
Thank you, George. Where was I? Test. Oh, so we say branch not equal to. It's very common, actually, to arrange your loops in embedded systems to end at 0. Sometimes we'll rearrange our whole loop so that our counter counts down to 0 because of the fact that branch not equal to automatically takes advantage of the fact that if the result of the previous arithmetic operation, the decrement, is 0, it won't branch.
So we want to make it go to 0, like instead of incrementing, we always...
Yeah, most of the time in loops, we start I equals 0, I less than 10. In embedded programs, we almost always go the opposite way. We start at 10 and go to 0. However, it's nice and easy. If you want to do something 9 times, you load up 9, you use branch not equal to, done. It's going to do it 9 times, whatever the body is. And again, the blue body here of the loop could be a zillion lines long. Doesn't matter. Okay? You just forget your glasses, or are you really confused? Because you're giving it the stink eye.
My contacts are
Okay. It's fine if you have a problem. You're just like, want to address it early on.
Yeah, I got it though. Yeah.
Okay. So again, it's just initializer, body, update, test. You guys think that you could write something that would do something in a loop? Abe?
What is
.org, okay, is a pseudo instruction. We talked about it, I think, 2 classes ago. All it means is start putting this at address 0 of ROM. Remember, when we turn on the processor, it always starts at address 0 and it begins executing. So we want to put our code right where it starts executing. That's all .org does. Okay, it just says put it at the start. Okay, so let's clear this out here. So, again, 4 parts. Initializer, body, increment or update. Could be a decrement, so we call it update. and then test. Your task, and I even give you a flowchart. All right. Write the program associated with this flowchart. The flowchart says write a program that calculates the result of 9 plus 8 plus 7 plus 1. Writes the sum, summation of those integers. I thought I was okay this morning. I woke up, felt better than I had past couple of days, but yes.
Is there a way to initialize multiple variables in one line, or do you have to do it separately?
You have to do it separately, and that is the nature of assembly language. Every instruction takes like one cycle, but to do anything of consequence, you need multiple instructions. So you can't do that initial block without doing 2 lines. All right, are we about done? How many people? Almost done? Almost done? All right. So, what was different about this? We have one extra variable. We have a sum. We're keeping track of the sum. Which register does my flowchart use to keep track of the sum? R17. So R17 is keeping track of the sum, and R16 pulls double duty not only as the counter, but also as the value. So, the first time through this loop, R16 is 9. So we take 9 and we add it to 0, and we get 9. And that gets stored in R17. That's 9. Then we decrement R16. So it was 9, now it's 8. Is 8, thank you so much. Nothing.
You like it?
Just wondering if you're spitting it. That's all.
Oh.
9. When we subtract 1 from 9 in this update block, that's going to affect the flags. So we saw already that probably we're not going to use the greater than branch. We're going to use the not equal to branch. So 8 is obviously not 0, so we jump back up to the main body of the loop, and then we add 8. So that gives me 17. We decrement this to 7. 7 is still not 0, so we jump back up. That's 24. Okay. Let's skip ahead. R17 is some number, and R16 is 1. Okay. It's 1. So we've gone 9, 8, 7, 6, 5, 4, 3, 2, 1. That's a total of 9 times through the loop. We decrement 1. 1 becomes 0. At that point, the Z flag is set, and we do not branch. We fall through to the end. So here's the solution to this. Here in our initial block, we have 2 LDIs. That's it. That's the only addition to the initial block. The actual body is almost the same as the last one, even though we didn't know why we were doing it back then. We're just using R17 to accumulate the result. So when you make a use of a register like this and it's always getting the results, always storing the result, we call that an accumulator. It accumulates the sum. The update is just a decrement, and in fact, let's call it 90% of loops that you write will usually use a decrement not equal to combo. Yes, Victor? Always branch if. So specifically, if you look at how it works, it's only going to jump if the Z flag is 0. Branch if equal branches if the result is equal. And it's specifically because of the way we do comparisons, right? We subtract. If I subtract 9 from 9, not real assembly code, but if I subtract 9 from 9, the result is 0, which means they're equal. If I subtracted 9 from any other number, I wouldn't set the Z flag so they wouldn't be equal. Yes?
So now, in the assembly code, can you do subtract R16 minus 1? Would that technically still work? Or
you could, because there is a subtract immediate instruction, SUBI. We'll talk about that, I think, next class, but it is an instruction you can do.
Two things. Well, R16 equals R16 minus 1. If I type in the code add R16 minus 1, is that wrong?
Well, it's wrong. It's wrong for one reason and right for a different reason. Okay, the reason it's wrong is because add must have 2 registers. There is no add register to number. That doesn't exist. Okay, now the idea of adding a -1 is a great idea, except there's no add immediate instruction either. There is a subtract immediate instruction, so you could subtract 1 from R16, but there is no add immediate. Okay, yes?
Is it possible to add like more than 2 registers, like for example, 4?
Nope, you would have to do it in 3 steps. Well, the first program we ever wrote was add 2 numbers. So you did LDI, LDI, add. When I asked you to add a 3rd number to that, you had to do LDI, LDI, add, load up the 3rd number, and add again. So it took 2 add instructions. So if you want to add 5 numbers, you need 4 additions. Okay, if you want to add up n numbers, you need n minus 1 additions. Other questions? Okay. So, you've got the code for writing 9 to 1. How would you modify that code to make it go 20 to 1? Give it a minute. Somebody else, when you think of it. What would you have to change about the previous code to make it work for 20? Victor? Yeah, you just change R16. You change the initial value to 20. Same code, Okay? Maybe these skills tests that I've been giving you about loops have some relevance. They make your life easier, I promise. Okay? So loops are awesome. Now, all of these loops have been based around the idea of a for loop, loosely. There's a few things that are different. A for loop in C has an initializer, a condition, an update, and a body where you do something. And so does this flowchart. Initializer, do something, update, condition, and then back. Now, strictly speaking, this flowchart is not a for loop. The one difference in a for loop in C versus this flowchart is the first time through a loop, it actually will do the condition before, right after you do the initializer. But for most intents, this is fine. Oh, yeah, I even write it down. Okay, so normally right after the init, we execute one conditional. Okay, so things that can get a little bit more interesting as you build on this. Let's say we want to add the odd numbers between 1 and 27. Sometimes it's not possible. In this case, you could rewrite the loop a little bit, but sometimes it's not possible to not go down to 0. So in this case, the difference in my update and test is the thing I want to call to your attention here. This is my update. Every time through the loop, I load 2 and I do an add. Okay, that's the update. Because I suppose I could do increment twice, but this is how I chose to do it. At the end of the day, it's still 2 cycles. I don't think it really matters. And my conditional, since I want to go up every time through the loop, I need to load up 27, subtract, and then do a branch if same or higher than. And again, carry clear doesn't tell you what you're trying to do. Same or higher than does. So we're saying, while R16 is less than or equal to 27, so our test is 27 greater than or equal to R16. So it is possible to count up. Obviously, it's a little bit easier. It takes a few less statements to count down because we can just, 0 is automatic. Okay, a decrement automatically gets us to 0. So that's loops. So we've done ifs, conditionals, either if then or if then else, and we've done loops. The last topic is functions. And before we get into functions, we need to talk about one programming concept called a stack. And we're going to introduce 2 new instructions, push and pop. Okay, so a stack is what you might think of as a stack of dishes. And I happen to have some change here. So as I take this change and I put it in my hand, I take a quarter and I put it in my hand. Then I put a penny on top of that. Then I take this dime and I put it on top of the penny. I'm making a little tower. Then I put a penny on top of that dime. Is it feasible for me to get that dime out from underneath this penny? Not really. I mean, maybe I could kind of, but not really. What I would have to do is first take off that penny, then I could get access to that dime. This is the concept of a stack. It's also what's known as last in, first out. A stack is just a block of memory, okay, that you put values into. When you put values in, there's this thing called this stack pointer. The stack pointer points to the next empty location. So the stack pointer points to an empty location. So if the stack pointer is pointing here, that means that there's some number there, and this is an empty location. There are 2 instructions that interact with the stack. Well, there are other instructions that interact with the stack, but these 2 directly operate on it. That's their sole purpose. If I push an instruction, do a push register, that's going to take the value in that register and put it into memory where the stack pointer points. So if I said that R5 was equal to 10, and then I said push R5, that's going to put 10 in that location, and then the stack pointer will now point to the next. So it's a two-step process. First, it puts something into memory, and then it decrements the stack pointer. It decrements it because down here, this is a high address. Maybe FF, FF, and up here, this is 0000. So it works from high memory to low memory. When you pop information, so I could say pop R1, first thing it does is it increments the stack pointer, and then it takes this value, this new value, and shoves it into R1. So R1 will now have 10 in it. Okay. The stack pointer itself is a special purpose register. It's actually two special purpose registers. Because RAM is so large, we actually need 2 bytes to address it. So there are 2 registers. One's called SPH, one's called SPL. They are in the I/O space, okay, which means we use in and out to access them.
So the pop R1, what is that?
Pop R1 gets something out of the stack. It's the equivalent of me taking something off of this stack of coins.
So would you have to continue to change that, like, or just pop R1 pulls?
So it's a 2-step thing. So not only does it get the data out, but it also updates the stack pointer every time. So if I were to say, like I said, pop R1 here.
So it takes that out and then puts in what the value of R1 is.
Nope. Back up.
Okay.
Push puts things into the stack.
Okay.
Pop removes things from the stack. So when you push something, data goes from the register into the stack. When you pop, you take something out of the stack and into a register.
Okay.
So what I did over here was I said pop R1. So since the stack pointer, let's redo this here. Let's say that 1, 2, 3, 4, 5, 6. That's what's in the stack.
Okay.
So I had to push something into the stack because the stack pointer started here.
Yeah.
The stack pointer always points to an empty spot.
Okay.
So when I push, the stack pointer now points here. So maybe I pushed R1 in. Okay, so R1 had 56. Now, let's say I pop R2. So the stack pointer, first thing it does is increments. So it no longer points to that empty space. Now it points here. And then it says, okay, get the value out of the stack and put it into R2. So now R2 has 56. If I say pop R2 again, that's perfectly valid. It decrements the stack pointer. Now it points here. Overwrites R2 with 34.
We have to go 1 by 1.
You can only do 1 byte at a time. Is that what your question is? Yeah, so if I wanted to pop 5 values off, that's 5 pop instructions. Okay. And by the end of this, I think we'll see us popping a few things. Yes?
So you can only take from the top, you can't take from like in the middle portion?
Not without some extra work. The pop instruction and the push instruction only operate on the end of the stack.
So let's say you wanted to pop like 1, 2, and you have to pop everything else.
You have to pop everything else first to get to 1, 2. It's everybody's heard of the Italian tablecloth trick. Go to a fancy Italian restaurant and they pull the whole tablecloth right out. That's what you can't do with a stack. In order to take the tablecloth off the table, you must take off all the glasses, all the candles, all the plates, all the silverware before you can touch the thing at the bottom. Okay? So a stack is not an Italian tablecloth trick. Okay, so let's do a practical example. Here I've got some code with some pushes and some pops. I've got memory showing up here. Okay, I've got a few registers showing up. So the first thing that I do is I actually tell the stack pointer where to go. the first 4 lines here actually write to the stack pointer high and the stack pointer low I/O registers. RAM end is a special thing that comes from the include file, and high and low grab the high and the low bytes of those. So as I execute, first R16 takes on the value and we output. So that sends the high byte somewhere to the middle of memory. We haven't finished updating the whole stack pointer until we update the low byte. Now the stack pointer is pointing somewhere at the bottom of memory. That's almost always where we put it. So now I do a couple of loads. I get some data into some registers, 10, 20, and 30. Then I push R20. R20 currently has 10. So 10 appears on the stack, and the stack pointer moves up 1. Now when I say move up, I'm really meaning decrement, but moves vertically up towards the beginning of memory. Then I push R21. What value is going to appear on the stack? 20. Yep. So R21 is itself the value 20. Then we push 30. So the stack pointer is pointing there. The next instruction is pop into R21. The only thing that can be popped is what's right on the top of the stack, which is a 30. So when I pop R21, it's going to take 30 and shove it into R21. It overwrites that value. Then I pop into R0. This is just to illustrate that just because you push from one register doesn't mean you need to pop back into that same register. You can pop into any register you want. And finally, I pop R20. Every time I do a pop, it first moves the stack pointer lower, which is an increment, and then it gets the value off. Okay? So that's the stack, yes?
Do you have to do that first bit of code every time you want to misrun the stack?
Once per program.
Okay.
Okay? You don't want to overwrite the stack if there's data on the stack. Now, our particular processor actually does this for you at boot time, but it's a good habit to get into. Okay? So, why do we have to talk about the stack? Well, because of how functions work. The thing about a function is that if you call it multiple times, you go back to wherever the call was. So here I've got a call on line 6. Now, a call by itself looks very similar to an unconditional jump. It's got an opcode and then a full 16-bit address. It just says, make the program counter A. And that's where the function is, down there. But the tricky thing about a function is when you're done with a function, you want to go back to where you were. So you were at line 6, you want to go to line 8. So here's how it does it. It uses the stack. When you are executing instructions, the program counter is incrementing by 1 every time. When you do a call, necessarily the program counter is going to have to change to A. A is where you're going. But before it does that, it looks at where it is. It's at 6. It says, what's my next instruction? It's 8. So it takes 8 and it puts it on the stack. It saves it on the stack. Then it overwrites the program counter just like an unconditional jump would. So call is an instruction that is an unconditional jump, but also has an unintended side effect, an additional side effect. It's not unintended, it's very intentional. But it's a side effect of storing the return address on the stack. So then here's your function. It does whatever. There is a companion instruction to call called return, R-E-T. R-E-T is an instruction that gets its branch address from the stack. So return does 2 pops and puts those 2 pops into the program counter. And that's all it does. So that's how a function works. When you were in C and you were writing printf and you were writing your own functions, at some level there was a stack, and when you were calling that function, the return address was put on the stack. In C, we even have a return instruction. A return instruction eventually turns into a return assembly instruction. Okay? So that's functions. And then it executes forever. So, functions are the easiest thing to explain between if and else. Okay, functions are pretty straightforward. You use a call, and a label is all you need to define a function. A label, a return, and a call together make a correct function. You call the label, it's unconditional. You return, and that brings you back. Functions can do anything you want them to do. In assembly, there is no facility to magically pass arguments to a function. In C, we could have an argument list. We could pass 50 things if we wanted. And we could return values from a function. We can't do that in assembly without a little bit of work. The simplest type of argument passing is you just have what's called a priori knowledge. You know beforehand that you're going to put some number in R21, and then you just assume that R21 has a value inside the function. That's what's happening here. We load up R20 and R21. This adds R20 and R21 together and then subtracts 3. So this function might be called add 2 nums, this is a very long name, minus 3. That's what it does. It adds 2 numbers and then subtracts 3. It's a mathematical function. But it assumes that the 2 numbers you want to add are in R20 and R21. It also assumes that when it's done, the result is going to be in R20. So when you call this function, beforehand, you have to have set up R21 and R20. After this function, your answer is in R20. It's just how you wrote the function. And it's up to you as the assembly programmer what registers you want to use. You can use any registers you feel like. Okay? So let's combine a few of these things into something you're going to need for the lab. This is our standard picture of what's inside the microcontroller, inside the 328P. The key feature of the processor is it has this circuit over here. This is 2 capacitors with a crystal. This crystal oscillates at some frequency. Our crystal oscillates 16 million times a second, or we say that it oscillates at 16 megahertz. Okay, oscillates at 16 megahertz. And here it is here. There's the oscillator. That is responsible for all timing through the processor. When you look on your assembly sheet and you see that something takes 1 cycle, that is 1 cycle of the clock. Now, how long does 1 cycle last? Well, the frequency is 16 megahertz, and frequency is inversely proportional to the period. So if you want the period, or the time in seconds of that clock, you take 1 divided by 16 million. 1 divided by 16 million is 62.5 nanoseconds. I did the math. This is one of those numbers you kind of want to have available to you. 16 megahertz frequency is 62.5 nanoseconds. There are some easier ones to know about. For example, 1 megahertz. 1 megahertz is itself 1 E6. So 1 over that is 1 E negative 6. What is 1 E to the negative 6? In terms of our SI prefixes, minus 3 is milli, micro. So that's just 1. I should say it's proportional to. Proportional to 1 microsecond. 10 megahertz is 0.1 microseconds. 100 megahertz, 0.01 microseconds. So powers of 10 are nice and easy to deal with. But so 1 megahertz, 1 microsecond. Most of the time when I want to do examples, I'll use 1 megahertz. because 1 microsecond is very easy to do math with. Okay, but so the title of this slide is time delay. If we want to delay for a particular amount of time, we are limited to what our crystal tells us. Okay. Now, eventually, we will get into the timer unit, but today we're just going to write some code to delay for a particular amount of time. First thing I want to do is let's just look at this code. This is in the time delay code, but it doesn't happen instantaneously. Okay. It does take some amount of time. Someone please look up, tell me how many cycles LDI takes. You think 2? I've got 1, 2, and 3. The answer is 1. It takes 1 cycle. What about add? How many cycles does that take? It also takes 1. So how many cycles does this code take? Well, it's not that complicated to figure out. You've got 5 instructions. Each one takes a cycle. It takes 5 cycles. So the question is, how long? This is 5 cycles. If I leave my units here, cycles, okay, how long does this take? Well, no matter what answer you give me, you're going to be wrong because I'm going to choose a different clock frequency than you assumed. You have to know what clock frequency you're running at in order to calculate time. So there's not enough information on this slide to determine this. Once I say, however, that your crystal frequency is 1 megahertz, now it's very easy to tell me how long this takes in seconds. Because I told you that 1 megahertz means 1 cycle executes every 1 microsecond. So for 5 cycles, that's 5 microseconds. Don't you see why I love 1 megahertz as a clock frequency? 1 cycle, 1 microsecond. Okay, now, how long does branch not equal take? Go ahead, look that up for a moment. 1/2 is absolutely wrong. It does say 1/2. You're absolutely right. What? It takes 1 or 2. Why would it take 1 or 2 cycles?
Because if it is equal to, it'll stop, but if it's not, it checks and then goes.
Right, because there's 2 different ways it could go. It could branch back to again, or it could fall through. That 2 is usually called a branch penalty. It takes 2 cycles if it has to go here. That's 2 cycles. It takes 1 cycle if it just goes to the next instruction. So, how do we determine how long this code takes? Yeah, we're going to have to do some calculation. Not just and the thing is, we can't just say 1 plus 1 plus 1 plus 1. That would be 4. 4 is wrong. We can't say 1 plus 1 plus 1 plus 2. That's 5. That's also wrong. No, you can't say 4 or 5 either. Because let's walk through this code for a second. Are you about to tell me that it runs multiple times? Yeah, let me go through it. When we first do this, R16 gets loaded with 100. We add R17 to R16. Then we decrement R16. So now it's 99. Is 99 equal to 0? No. So does this branch go up or down? Goes up. So now we do another add, and we decrement. Now we've got 98 bottles of beer on the wall. Then we've got 97, 96. This is going to go on for some time. We're actually executing this instruction and this instruction and this instruction more than once. This is a loop. So it's not enough to just look at it and say, all right, it's going to execute however many the sum is. We need to add in a bit more information. So because this is a loop, we need to first identify which instructions are going to be executed multiple times. And I've done that. So anything between the loop label and the branch are going to be executed multiple times. the next thing we need to do is we need to analyze and say, how many times is this loop going to execute? 100. Because we used a very simple thing. We used our load a particular number, decrement not equal to branch. We know that this is going to execute 100 times. So when we do this, we take those instructions that are included in the loop, we multiply their machine cycle time by 100. Now, 1 times 100, that's pretty easy. That's 100. 1 times 100, that's 100. 1/2 times 100 is where most people start to go, what? It's actually not 200.
199.
It's 199. The way I think of it is it's going to go through this loop 100 times, which means 99 times it's going to branch. Branch. It's going to branch. 1 time out of that 100 times, it's going to not branch, which means 99 times it needs to pay the branch penalty of 2 cycles. Only 1 time will it do that. Now, you could say that this is 99 times 2 plus 1, which I find causes people more problems. What I say is this is 2 times 100 minus 1. I overestimate first. I say, all right, we've got 100 times through the loop. I'm going to pay the branch penalty 100 times, and then I'm going to take back 1 because I don't actually pay it 100 times. In this kind of an example, it doesn't really cause too much problems, but it does help a bit because one of the things that I should never forget is that there is this instruction. That instruction does exist. It's part of the delay. And it just so happens that 1 and -1 cancel very nicely. So what's my total number? Well, 2 times 100, that's real tough math. And then 100 plus 100, 400. 400 cycles. If I had said 2 times 99, 2 times 99 is 198, plus 1 is 200, no, is 199. The less math I have to do in arithmetic, the better I feel, okay? Because that's where I tend to make mistakes. Now it becomes really important. Well, hold on. Before it gets really important, one more instruction to introduce to you today. The no-op instruction. No-op does nada, nothing. Doesn't affect the flags, doesn't affect the registers, doesn't affect memory. It does nothing but waste a cycle. So if you're intentionally trying to delay time, it's perfectly valid to use a no-op. So here I've got 2 no-ops. It loads up 50, executes a no-op, a decrement, a branch not equal to. So the things that are in the loop, the instructions that are in the loop, are anything between the label and the branch. How many times is this loop going to run? 50. So what do? 1 times 50 is 50. That's 50. That's 50. Here I take 2 times 50, 100, minus 1. And it's very important to not forget the instructions that aren't in the loop because it's part of the delay. So overall I have 250. Pretty straightforward. Well, of course, it's never going to be that simple. Not in Dr. Biles' course, no. Here, things get a little bit more interesting. Notice I have 2 labels. I have 2 branches. Let's just look at where these branches go. Here, branch not equal jumps to L2. Branch not equal L1. This is an example of what's called a nested loop. One loop is entirely inside of another loop. So these instructions are themselves a loop. But that loop is going to run multiple times. It's inside of a larger loop. The analysis for this one gets a little bit more complicated. We always start with the innermost loop doing our analysis. So L2, how many times is L2 going to run? What is the counter variable for loop 2? I meant what register? It's R16, right? You know that because it's in the update. And R16 outside the loop gets loaded with 50. So each of these instructions is going to get multiplied by 50. Then the outer loop, how many times is the outer loop going to run? 20, because R17 is the loop variable, and we load it with 20. So when it comes right down to it, we've got something like this. Some things are going to be multiplied many times. There is a better way of doing this, there are better ways of doing the math and worse ways of doing the math. One is less prone to error. Order of operations in doing this math is everything. It's the difference between a completely wrong answer and something that resembles the truth. Okay? When I do this, I always start by figuring out what the inner instructions are first. So this is 1 times 20 times 50. 20 times 50 is itself 1,000, 100, 1,000. Okay. So this is 1,000. This is 1,000. Here, this is where stuff gets really complicated, and the order matters. So this loop, okay, by itself runs 50 times. So that's 2 times 50 minus 1. Then I know that it overall runs 20 more times. Okay? 2 times 50 minus 1 times 20. Your first inclination might be to come up with a hard and fast number here. Okay, 2 times 50 is 100, that's 99. 99 times 20 is something. I would have to pull out a calculator. Better is to just expand it. So 2 times 50 minus 1 times 20 becomes 2 times 50 times 20 minus 20. Okay? Much better way of doing that. And that covers all the things in the inner loop. The outer loop, 1 times 20 is 20. This is 20 times 2 minus 1. This is 20. That's 1. So when you do all of this out, I just want the eraser. I want to erase this here for a second. You do it all out and you add things. You've got 1 plus 4 20s. You've got a 20 here, a 20 here, 2 20s here. Plus, oh, I did it a little different. I did 5 times 50, 1, 2, 3, 4, 5, minus 1 times the 20. It's all the same. Okay, this was adding up those, because that's how long that loop takes, multiplying it by 50, and then subtracting the 1 to deal with the branch penalty. And then all of that times 20. Finally, there's my minus 1. Why did I do it that way? Heck of a lot easier to deal with. Because now you expand out that 20. So you have 5 times 20 times 50 minus the 20 from the negative 1, minus 1 and plus 1. So tons of stuff cancels. 5 times 20 times 50 is pretty easy math. Okay, 20 times 50 is 1,000, times 5 is 5,000. 4 times 20, all off on its lonesome, is 80. 1 minus 1 cancels. So we got, oh, the 80 and the 20 cancels. So all told, 5,060. What? All right. If you're shaking your head right now, do the math. Do it out 2 or 3 times. Try it a couple of different ways. You know what the answer is. do it out. I'm not collecting it for homework, but it's your due diligence. Okay? If you want to go over it, come see me in my office. You will.
Why did you multiply 5 by 20 by 15 minus 20, but not like, why isn't 5 times 20 and 15 times 20 as well?
Let me clear some space here, and we'll go over it. So the way I did it here was I said, all right, all told, the inner loop is going to be 5 cycles every time through the loop. It's 3 plus 2. Now I know that it's going to run 50 times. So that's 5 times 50. But I know that I actually have overestimated by 1 cycle, because the last time through this loop, it's going to fall through. So there's my minus 1. Okay? But I also know that this loop is going to be executed 20 times. So I take 5 times 50 minus 1. That whole quantity has to be multiplied by 20. It would be an error to forget about the fact that it's the whole quantity times 20. So then when I expand it, that's where the minus 20 comes in, because it's negative 1 times 20 is minus 20. And so then it's 5,000. Because 5 times 50 times 20 is 1,000. All right, we are actually a little ways behind. What I want to do here, oh, it's not on this slide. Discard my ink annotations. We're a little behind. I actually wanted to be talking about I/O today, I believe. Today is the 19th. Yeah, I wanted to be talking about input and output, but we lost some time with that guest lecturer. Those extras? Oh, that's homework. Okay, so homework will be available to collect as you leave. Read the chapter 4 on input and output. We're going to go through it fairly quickly on Thursday. Your homework is in the lab. Homework 2 is listed inside of the ASCII lab. It's at the end. So your job is to go and look at it, because on Thursday you start the ASCII lab. All you need to do the initial homework part is loops and functions. And a lot of things are given to you, example functions that you can use in your code. So I encourage you to look into that. I will see you. Oh, you all received an email with the open lab hours, right?
Yep.
Today, it's open lab all afternoon, right? Most of the afternoon is open lab.